today I'm kind of talking mainly about generative modeling, but kind of let me give you a general overview of my research first, which will also come up later in the talk. So in general, I'm kind of interested in kind of quite a wide range of mathematical tools, ranging from applied analysis to numerical analysis, optimization, as well as data science. And in fact, this can be useful in a wide range of applications, ranging from biological applications, where, for instance, what is very common is that you have some more difficult data structures. For instance, you have some underlying networks which can be described using graphs, and then we want to both do some mathematical analysis as well as some numerics to understand better how we can explain complex flows in these underlying networks, which kind of arise, for instance, in the context of blood circulation systems. We've also looked at different engineering applications, but more recently, my group mainly focuses on applications in climate science, where, in fact, what is very nice in this area is, first of all, it's all based on differential equations, and there's also a huge amount of high quality data available, since our weather has been recorded for the last 40 years or so. And in particular, there are different kinds of aspects which we've been looking at, for instance, in the context of cloud organization, where we kind of wanted to better forecast the clouds, which have a big impact on our weather. But kind of having said this, today's talk will mainly focus on a specific aspect of machine learning, rather than on the more applied directions. And in particular, we're interested in generative modeling, which kind of has the aim of generating data, roughly speaking. So what we want to do is we want to learn some probability distributions given a finite set of samples. So you can think of this as we already have a number of images, for instance, like a large number of images of dogs, for instance, and now we want to generate more images of dogs, but not by averaging all the pictures we have, but by producing realistic looking pictures of dogs, for instance. And if one looks kind of into the literature with regards to that, then there have been different types of approaches suggested in this context, when one has the aim of learning the probability distribution and then taking samples from that learned probability distribution. So one broad class of models are likelihood-based models, where kind of the key idea is that one explicitly models the probability density and maximizes the likelihood. So there are, in particular, variational autoencoders, normalizing flows, and autoregressive models, which can be kind of classed as part of these likelihood-based models. Another class of models which one could consider are implicit models. So rather than modeling the probability density explicitly, which kind of comes with some difficulties, which I will outline later on, one could try to sample without actually knowing the density. And here, a promising example are generative adversarial networks, which were proposed by Goodfellow in 2014. And later on, as part of the talk, I will also go into more detail on one of our research regarding Wasserstein generative adversarial networks. And last but not least, more recently, so-called score-based models have come up, which have actually proven to be very powerful in generating high-quality samples. And here the key idea is to estimate the gradient of the density instead of the probability density function itself. So broadly speaking, we kind of have all these different types of approaches now, which we could consider to learn a probability distribution and to sample from it. But the question is, which of these different kinds of approaches should we consider now? And when kind of looking into those likelihood-based models, in fact, it turns out that there are strong restrictions on the architecture which are required, because remember, as part of those likelihood-based models, we want to approximate a realistic probability distribution. And this means we need to make sure that the integral of the probability distribution is equal to 1. So we need some appropriate normalizations. And in addition to that, we also need to make sure that it kind of satisfies basic properties of a probability distribution, like, for instance, non-negativity and so on, which kind of comes with some difficulties with regards to ensuring this. And this was actually also one of the key reasons why different types of approaches have been suggested in the literature. And in particular, implicit models came up. And in fact, generative adversarial networks have been one of the most promising modeling approaches in recent years. However, they also come with some difficulty, namely with regards to their training. They can be extremely unstable, which might result in mode collapse. However, the Wasserstein GAN, which is kind of related to the Wasserstein distance and as such related to some kind of mathematical foundations, was often motivated as kind of one of the best generative adversarial networks. And as a mathematician, we were very interested in kind of understanding better whether Wasserstein GANs indeed work better than any kind of other GAN, or whether this is absolutely not related to the Wasserstein distance. And so as part of the work, which I'm going to talk about later on, we will go into more details how these generative adversarial networks work and their relation to Wasserstein GANs and the Wasserstein distance. And so more recently, another type of generative models came up, these score-based models. And in fact, they feature a key difference to all the other type of modeling approaches, namely that they don't require normalizing constants, for instance, as in the case for likelihood-based approaches. And in fact, also in generation tasks, they surpass Wasserstein GANs, which is kind of extremely good. And last but not least, also from a mathematical perspective, they actually offer theoretical guarantees, as they are based on probability flow, ordinary differential equations, stochastic differential equations, and in fact, one can also derive the associated Fokker-Planck equations for these types of approaches. And so they are in general very promising to study a bit further. And I will also go into more detail later on about our recent work with regards to these score-based models. So kind of just to get started, let's look at generative adversarial networks first, and more specifically on Wasserstein GANs, where we want to understand a bit better why they work. And in fact, it also turned out that they don't really approximate the Wasserstein distance, even though they were motivated by this. So let's look a bit into how generative adversarial networks work in general. So to do this, we consider two different neural networks which compete against each other. On the one hand, we have a generator which takes as an input some random noise and generates some realistic looking images. And on the other hand, we have some real data giving us real images. And so the task of our second network, the discriminator, is to distinguish between those fake images generated by the generator and the real data. And so overall, we have these two neural networks, a generator and a discriminator, which have competing goals. So the goal of the generator is to produce samples which are fake, but which look as realistic as possible to the true data. And the aim of the discriminator is to distinguish between true and generated data. So to phrase this a bit more mathematically, we have two neural networks, a generator and a discriminator, which compete against each other. The generator we denote by G theta, where the weights theta are trained as part of our training. And this generator can be regarded as a function going from some latent space Z, which is equipped with a multivariate Gaussian distribution and goes into the data space. So by data space, you can always think of, for instance, some image space. And with regards to the outputs of the generator, as it takes kind of some set in set, which is sampled from that Gaussian distribution. We denote the output by G theta of Z, and we can also associate it with some kind of generator distribution. And here the key idea is that we want to compare the generator distribution P theta with the target distribution, which we denote by P star. And as I said before, the key idea of the generator is that it produces some fake samples which satisfy this generator distribution, and the goal of the generator is to make them resemble the data from the target distribution. And then on the other hand, we consider a second neural network, which we call discriminator d alpha, where we want to train the weights alpha, going from the data space to some real number. Here, with regards to the real number, one could regard output 1 as a real sample and 0 as a generated sample. And X is again the data space, so depending on which sample we have as an input, we will get the associated outputs. And here we want to train these weights alpha to distinguish between samples drawn from the generator distribution as well as from the training data. And so overall, one can already see that there's a strong interaction between this generator and the discriminator. To phrase this a bit more mathematically, what we basically want to do here is the discriminator, d alpha with weights alpha, needs to be trained to maximize the probability that real data is classified as belonging to the real data set. So this means if we have some X from the target distribution P star, we want to maximize over all alpha the function d alpha of X. And on the other hand, if we have a fake image, which is denoted by G theta of Z, where Z is from that multivariate Gaussian distribution, then we want to minimize this associated probability so that we want to consider the minimum over all alpha of d alpha of G theta of Z. So this is kind of our general update rule for the discriminator. And then based on these key ideas, Goodfellow and others introduced the vanilla GAN. where the discriminator objective is essentially based on these two update rules, which we have kind of just discussed. So we want to maximize overall alpha, the expectation of the logarithm of the alpha, plus the expectation of the logarithm of 1 minus the alpha of g theta of z, which kind of directly reflects those two conditions we kind of previously introduced. And then with regards to the generator's objective, since this is supposed to compete against the discriminator, all we need to do now is we want to train the generator weights theta, and as it's competing against the discriminator, we now want to find weights theta so that overall this objective is minimized. So now that we've kind of looked at the generator's objective, in fact, it turns out that this is equivalent to minimizing the Jensen-Chen divergence between the target distribution as well as the generator distribution. And so this kind of arose the question whether one could actually also look at different types of distances instead of the Jensen-Chen divergence. And these kind of questions on which metric to choose in this context mainly come from the fact that for the vanilla GAN, where the Jensen-Chen divergence is considered, there were some issues with regards to training. In particular, it can be shown that the optimal discriminator leads to vanishing gradients as soon as the alpha approaches the optimal discriminator, which is of course not desirable because then no updates will take place any longer during the training. And secondly, what can be observed is that the Jensen-Chen divergence is maximized when two distributions have disjoint support. However, what actually happens quite frequently in practice is that two distributions might be closely related to each other, but their supports might be similar but not identical to each other. And this is in fact motivating the use of the Wasserstein distance, which decreases smoothly as the supports of the distributions converge to each other, and motivated the introduction of the Wasserstein GAN, where in fact kind of the objective is written very similarly as before. So one has kind of again one term which is relevant for having true images as input and then computing the associated expectation, as well as another term dealing with the fake images and their respective expectation when going through the discriminator. And so overall, this kind of results in writing the Wasserstein GANs objective as a minimization problem over the Wasserstein 1 distance between a target distribution and the generator distribution. However, as you kind of notice when one kind of writes down this formulation here in detail, is that previously for the vanilla GAN objective, we were kind of just looking at all alpha, whereas for obtaining this equivalence between the Wasserstein 1 distance and the respective formulation here on the left-hand side, what we actually need here is we need to consider all one Lipschitz functions as our discriminator now, which computationally can actually cause some issues when kind of looking at this formulation here on the left-hand side as an optimization problem. So kind of to look into this in a bit more detail, what we kind of have now is we want to understand this Wasserstein GAN objective a bit better. And in particular, what we kind of already noticed is that there are some difficulties associated with this maximization problem of all one Lipschitz functions. In particular, it's impossible to optimize over the set of all one Lipschitz functions, but we kind of need to incorporate this as part of some regularization term as accurately as possible. And secondly, what we also observe is that generally speaking, we don't have access to the full measures of the target and the generator distribution, but only to finite samples. And so these can be, for instance, the associated empirical distributions. However, this kind of raises the question to what extent actually the associated empirical distribution would converge to the full measure and how one kind of deals with this with regards to the associated expectations which are considered in our objective. And so having kind of these two challenges, a Wasserstein GAN algorithm has already been proposed. And so our main motivation was to understand better to what extent we are actually able to approximate the Wasserstein 1 distance, even though we are facing kind of these two challenges. And so for this, let's look at the Wasserstein GAN algorithm with gradient penalty in a bit more detail. So what we observe in here is that on the one hand, we have some kind of outer loop where the key aim is to determine optimal weights theta, and we have an inner loop which deals with two auxiliary functions. So on the one hand, we have our inner objective, and on the other hand, we have some regularization term to make sure that we are considering all these one Lipschitz functions. And these two auxiliary functions can then be composed into a loss function with some regularization parameter lambda, which basically shows us to what extent this regularizer of one Lipschitz functions is satisfied. And overall, the hope is that when just looking at this first auxiliary function, that after training, it will be roughly speaking close to the Wasserstein 1 distance between the target and the generated distribution. And so as a first step, let's look at this in terms of simulations. And what we observe here in the top picture is that we consider different regularizing constants for this one Lipschitz constant. And in particular, if the regularization term is small, then we observe that the Wasserstein distance is kind of around 4 after 300,000 iterations, whereas for all the other lambdas, it's kind of roughly speaking around 1. However, we are aware that not necessarily the one Lipschitz constant is equal to 1, so one can also try to estimate this accordingly and then normalize the Wasserstein distance. And so after this normalization, we kind of still see that for all these different values of lambda, we kind of come up with a Wasserstein distance which is slightly smaller than 1. However, it turns out that for the fixed finitely supported distribution we considered, the correct value of the Wasserstein distance between target and generated distribution should actually have been 41, because for these fixed finitely supported distributions, we can actually compute the Wasserstein distance directly. So there's kind of a big discrepancy with what the Wasserstein GAN algorithm gives us and what the actual value should be. To understand this a bit better of what's going on, one can base these investigations on potential sample complexity issues, and in particular, it's known that the sample Wasserstein distance concentrates very well around its expectation. So let's understand a bit better what this associated expectation is actually like. And in that context, intrinsic dimension actually plays an important role, but let's assume that we kind of choose our dimension for the data sets we consider, like cell lab A, which is known to be around 20 accordingly, and then run some simulations again. And here, what we did is we considered an empirical study of the sample complexity where we varied the number of samples, and as the number of samples becomes larger and larger, as expected, the Wasserstein distance becomes smaller. However, if we kind of consider two different empirical distributions drawn from the same underlying distribution, we would hope that eventually the expected Wasserstein distance between those two distributions is close to 0. However, when kind of seeing these types of plots, when kind of considering something like 10,000 samples, this is in fact very far away from being 0. And so even on the logarithmic scale, this kind of doesn't really change much. So if one wants to extrapolate this a bit further, then one actually sees that to get a reasonably small Wasserstein distance between these two different empirical distributions drawn from the same distribution, then we end up with, roughly speaking, 10 to the power 50 samples, which is kind of impossible to do in practice. So this definitely demonstrates that there are some sample complexity issues going on. However, we believe that these don't fully explain the ongoing issues. And to study this a bit further, we also studied the minima of the batch Wasserstein distance. And here, what was observed in the experiments is that when looking at empirical distributions of the target distribution, as well as some other distributions, like for instance, another empirical distribution drawn from the target distribution, then we obtain, roughly speaking, an expectation of 50.67. However, if we kind of compare the expected Wasserstein distance between the target distribution as well as the average phase, which you can kind of see here in the middle, then this is around 47. And if you compare the target distribution as well as the geometric k-means clustering, which you can kind of see in here, then the expectation gets even smaller. And we also looked at this from a more mathematical point of view, that it turns out that those k-centroids of geometric k-medians clustering are minima. And so this kind of shows another issue which arises with regards to the batch Wasserstein distance, that we would have hoped that empirical measures drawn from the same distribution are very small, but in fact, these drawn from the k-medians clustering ended up to be much smaller. So what is actually going on in this context, and what we believe one could kind of explain this with is failures related to the L2 distance, which comes from the fact that, in fact, with all these different examples, we mainly focused on the Wasserstein distance between distributions for images. And if we want to kind of calculate the associated Wasserstein distance, then what we are basically doing is we are looking over minimizing permutations sigma and summing up some kind of L2 distance in that context, where we basically here compute the L2 distance between different pixels of our images. However, the L2 distance is known not to be very good as a perceptual distance, and to kind of illustrate this a bit better, why an L2 distance is not a desirable distance in that context, is that one could kind of look at some kind of reference picture as well as a slightly altered picture. And for the human eye, the first two images look very similar to each other, but kind of have an L2 distance of 62. However, a completely different image when compared to the reference image can achieve smaller L2 distances, and this is kind of reflected in all these different examples as well. So kind of overall, what we noticed is that, in fact, the training of Wasserstein GANs fails to approximate the Wasserstein distance, and to some extent, this can be explained by those sample complexity issues. However, they don't fully explain what's going on. In addition to that, it turned out that the Wasserstein distance has undesirable minima due to its connections to geometric k-means clustering, and as such is not a desirable loss function. And so overall, there are also some fundamental problems with using the Wasserstein distance due to the underlying Euclidean metric. So after having kind of looked into this problem of Wasserstein GANs, let's dive into some other more recent type of approach, namely score-based diffusion models. Which
Lisa Maria?
Yeah.
Can I just interrupt and ask for the to explain the title of the paper to which it is related? Because you say Wasserstein GANs work because they fail. So I understand that they fail to approximate the Wasserstein distance, and also this L2 distance is not appropriate. But why do they work?
Well, as has kind of been observed in the literature, GANs in general work very well, but this is nothing specific to the Wasserstein distance itself, as it was kind of motivated previously, but rather the fact that the way they are designed helps generate good-looking samples.
So even though, I mean, the loss function is not well approximated, as the true one that one would like to have, and even though this L2 distance doesn't seem to be appropriate, they still work, but yeah.
Exactly.
But there's not a good explanation for that, because one would say, okay, what they should actually produce is not produced, but still they work. So
well, kind of, if they did what they were supposed to do, then they wouldn't work. Like, that's kind of more our findings, that if they minimize,
if they really approximated well the Wasserstein distance, then you would produce,
nothing would work.
Mm-hmm.
Because as we kind of looked into the Wasserstein distance in more detail, this is kind of one of the key issues which kind of arose.
Because of this L2 thing? Or...
Exactly.
Okay. Mm-hmm. Okay, thank you.
So let's dive into something where we have many more mathematical foundations, and these are score-based diffusion models, where kind of the key idea is that we combine stochastic differential equations, probability flow ODEs, and mean field dynamics. And when kind of studying those score-based diffusion models, one usually introduces a forward process and a reverse process. So in the forward process, the key idea is that we have some given real data, for instance, the picture of a dog, and then we add more and more noise to it. So as you add more and more noise to it, as kind of shown over here, you get, in the end, you get a very noisy image. And then what is very nice is that there exists a theorem by Anderson, which also introduces an associated reverse process. So instead of looking at this forward SDE, where we go from data to noise, we can also go from noise to data through this reverse SDE. However, there's one difficulty which arises, namely that we need to know this score function, or if we don't know it, we need to learn it appropriately. So for the forward SDE, we assume that f and g are some kind of given functions with some initial distribution. So this can be kind of solved forward in time. And then for the reverse SDE, we can kind of write it down as previously. And what is very nice in this context is that the forward SDE and the reverse SDE have the same underlying distribution. And so the key idea is that one samples from the reverse SDE, going from noise to real data, so that we're able to generate realistic data by solving this reverse SDE.
And sorry, the P here is the distribution.
Yes.
The density.
Yes, the density.
Okay.
Like in the machine learning community, distribution and density are often kind of mixed up.
Yeah. Okay.
But yeah. So on the one hand, we kind of have this forward SDE and the reverse SDE. And in fact, one can also write down an associated probability flow ODE, which again can be equipped with some kind of initial condition, or equivalently, we can look at the associated terminal condition, because the key idea is that for the forward SDE, we kind of start with some initial distribution, and then for the reverse SDE, we start with some terminal distribution and then kind of go backwards in time as t becomes smaller until we are kind of arriving at t equal to 0. And so for the probability flow ODE, one generally also starts with terminal distribution and then rewrites this probability flow ODE to kind of go from t equal to capital T to t equal to 0. And one key problem with solving this reverse SDE and the probability flow ODE is that we need access to this gradient log density. And this can be done through neural approximations. So the key idea is to come up with some approximations of the gradient log density. And here the idea is to minimize the weighted Fisher divergence, which is also referred to as a score matching objective. However, in general, we do not have access to the ground truth. And so alternatives have been proposed, namely, in particular, the denoising score matching objective, where the key idea is that this gradient log density of P of xtt is replaced by some appropriate conditional density, which you can kind of see in here. And the nice thing about this alternative is, in fact, that the score matching objective and the denoising score matching objective are equivalent to each other when minimizing them, because they can be written as the denoising score matching objective being equal to the score matching objective plus some constant, which kind of doesn't really matter when we're considering optimizations. And in fact, this is kind of the first ingredient that we can look at the denoising score matching objective. And another issue we are facing is that in general, we want to come up with these neural score approximations which are realistically approximating the gradient log density. And in particular, it turns out if you're kind of just considering the approach I have mentioned previously, then S theta is in general not conservative, and as such, it can't be a gradient field of any function. And so this approximation of S theta being, roughly speaking, a gradient density doesn't really hold. However, one can learn a potential model instead and approximate the log density up to some normalizing constant. And then one can kind of show that everything is fine and the underlying mathematical properties of a gradient field actually hold. And this actually also motivates us to focus on log densities in our analysis rather than on the densities itself. However, we also showed how one can kind of go from those log density estimates back to the original density estimates. So what we have kind of seen so far is that on the one hand, we have this reverse SDE where we didn't have access to this gradient log density. This is the reason why we looked at neural approximations and want to approximate this gradient log density now using the denoising score matching loss. And now we have kind of a reverse approximate SDE if we kind of do this appropriate replacement. As a next step, we can also do this exactly in the same way for the probability flow ODE, where again, we consider the approximations of the gradient log density. And last but not least, we can also do this for the associated Fokker-Planck equations. As the limit of our samples goes to infinity, one can kind of write down both a forward Fokker-Planck equation for the underlying distribution as well as an appropriate approximation. So this gives us kind of a big zoo of equations. And in fact, finally, since I've said before, we are not really interested in the densities, but in the associated log densities. One can also do this approximation by considering the associated log densities and write down the log Fokker-Planck equation as well as the appropriate approximations. This kind of results in this big zoo of equations to deal with. And so the key idea of our approach was now to better understand how the solutions to these different approaches actually differ from each other. And in particular, we focused on the differences between the probability flow ODE as well as the reverse SDE. And here we wanted to compare this with Fokker-Planck type of residual, or more precisely the log Fokker-Planck residual. So this residual basically captures our log Fokker-Planck equation. And what we kind of showed analytically is that under relatively weak assumptions on our F and G and provided we have a neural network which satisfies this log Fokker-Planck residual sufficiently well. We could show that the Wasserstein 2 distance between the P theta ODE, which is a solution to the probability flow ODE, and p theta SDE, which is the solution to the reverse approximate SDE, becomes relatively small. So in fact, the Wasserstein 2 distance between those two distributions is smaller than c times delta for some constant c independent of delta. So in particular, this means that if kind of our Fokker-Planck equation is satisfied very well, then also the Wasserstein distance between the probability ODE distribution and the SDE distributions becomes very small. So to kind of see this in practice, we kind of studied the Ornstein-Uhlenbeck process. So in that case, f is equal to minus x and g is just the constant one function. And then we can write down the precise form of the log Fokker-Planck equation in that context, as well as a loss function, which kind of consists of the denoising score matching loss plus some regularizing constant times the residual of the log Fokker-Planck equation. And so if this WR becomes large, then we expect this residual to be very small. So the Fokker-Planck equation is satisfied very well, whereas otherwise the Fokker-Planck equation is not satisfied so well. And so we looked at this for different target distributions, namely the Gaussian mixture, circles, and checkerboard. And what we observe in here now is that you can see different values of WR. So for WR being equal to 0, this means that we're just considering the denoising score matching loss and compare the ODE and SDE solutions. And in fact, for all these different examples, one can kind of see quite big differences between those, whereas as WR becomes larger, this is equivalent to the associated log Fokker-Planck equation to be satisfied very well. The ODE and SDE distributions kind of coincide very well for all these different examples. And in fact, this is precisely what we also showed analytically, that if the Fokker-Planck equation is satisfied very well, then also the samples are very close to each other. However, what is also worth noting is that even though the Fokker-Planck equation is satisfied very well now, the quality of the samples, in particular with regards to the SDE ones, decreases as the Fokker-Planck equation becomes better satisfied. So for those first two examples, one can't really see this so well, but for the checkerboard, for instance, one can definitely see that as WR becomes larger and the Fokker-Planck equation is better satisfied, then we don't really have this classical checkerboard pattern any longer, but a smooth version, which in fact also makes sense because the Fokker-Planck equation wants the solutions to have at least some kind of smoothness. So kind of just to sum up this part of my talk, we kind of looked at score-based diffusion models where in particular we looked at the zoo of all these different types of equations ranging from probability flow ODEs to reverse approximate SDEs, and in particular we looked at the differences between the associated densities for the reverse approximate SDE and the approximate probability flow ODE. We showed analytically that there are some discrepancies with regards to the Wasserstein distance between those densities, where we use the Fokker-Planck residual as a regularization term. And we also showed in our numerical simulations that if the Fokker-Planck residual is satisfied, then our simulations for the SDE and ODE solutions become much closer to each other, as also demonstrated analytically, while this penalization with this Fokker-Planck residual also means that overall the quality of the SDE distribution actually degrades as the Fokker-Planck residual is better satisfied. So I hope that kind of as part of this talk, I could show you that in the field of machine learning, there's actually quite a big need of studying these different concepts more from a mathematical perspective, as for instance, with the score-based diffusion work, one needs kind of some inputs from applied analysis as well as numerical analysis and data science and machine learning. And hopefully, eventually, these results can also be applied in a range of applications. Thanks a lot for your attention.